Sergey Alexandrov about modularity of Calabi-Yau threefolds. So please.
Thanks. So I recall you that last time we stopped at the crucial result, which underlies all the progress which I'm talking about, which is this equation, or more precisely, it's an expression for the completion, modular completion of the generating function of rank 0 dt invariants. And the claim is that the expression on the right-hand side must be modular form of this particular weight. So this is the restriction on the on rank 0 dt invariance. And just let me say a few words about the structure of this equation without going much into details. So you see that there is this second term, which is starts from sum over n from 2 to r. So if r is equal to 1, the sum is absent. So we return to the pure modular case where there is no modular anomaly, and if r is larger or equal to 2, there is the second term which determines the modular anomaly of the generating function. And the structure is very simple. So you see that there is a sum of decompositions of this magnetic charge P into components, and this is like sum over possible decomposition of our divisor. And from the physics point of view, it's like sum over when you decompose a bound state in constituents, so sum over all decompositions. And once you have this decomposition, then there is just a product of generating functions corresponding to these constituents. And of course, the most important object is this coefficient r. And this is a quite complicated object, but we have an explicit expression for it. And just in words, this is an indefinite theta series on some complicated lattice. And the kernel of this indefinite theta series is determined by a sum over certain types of trees, which are weighted by sine functions and these generalized functions which I introduced last time. This is why I had to introduce this indefinite theta series and generalized functions, because they appear explicitly in this story and determine the main equation. Okay, that's it. And yeah, I will not give you the explicit expression for this coefficient. Actually, I have it on the next slides for in a bit simpler situation. So we will see whether we will look at it or not. But now let me also mention where this result can be applicable. So actually it was derived just using two assumptions. So first assumption is that our Calabi-Yau is compact. And the second assumption was actually done on the divisor, which we consider, which is labeled by our vector PA, and it was assumed that this corresponds to ample divisor. So what this means in practice, just two conditions. So from these two conditions follow. One condition is that so with this divisor we have a lattice lambda p. So I remind you this is H4 of Calabi-Yau Z, and it's equipped with the quadratic form kappa AB, yeah, which was kappa ABC PC. So if divisor is ample, what this means is that this quadratic form is non-degenerate, and it has signature, which is 1 P2 minus 1. And this is why we have indefinite theta series in this story, because you see there is this 1 here, and it precisely corresponds for the appearance of minuses in, well, here it's plus, but it's just because of conventions. So it leads to minuses in the signature of quadratic forms appearing in theta functions. And so this is one thing. And the other consequence of the ampleness is that P cube, which is just kappa ABC, PA, PB, PC, is strictly positive. But now I would like to claim that this equation, although it was derived using these two assumptions, actually somehow holds in a much more general situations and have generalizations which are completely unexpected. And why they hold, it's not clear, but somehow, well, all calculations show that they do hold. So first of all, how can we relax this assumption? So first we can take our divisor, say dp, to be not ample but only effective. So in particular, this can lead to the fact that our quadratic form can be degenerate. And still, there is a way to define the equation even in these situations, this formula for the completion. And also, PQ can actually become zero. And in this case, actually, what happens is that instead of just generic mock modularity, what happens is that our generating functions become quasi-modular.
Sergey, I'm a bit confused. You're talking about some formulas which do not make much sense because there are definitions of the objects of generating series, and I'm more interested to know how this abstract generating series become so concrete that you can write them in terms of indefinite theta function.
This will be the next step, how we solve this equation.
But not actually, how to solve, how we prove that the generating series of whatever Donaldson-Thomas or Gromov-Witten invariants, why they can be written in such a way. For compact Calabi-Yau, there is no way to compute explicitly in general, like, I don't know, Gromov-Witten or DT invariants, because you don't even know what kind of T structure you use.
So what I will explain to you later, is that I can use these equations to find generating functions, in particular for compact Calabi-Yaus. And at this point, I just use the equation, some other techniques to find the generating function. So I don't know what you want from me to prove at this point. But I can check, to produce very non-trivial checks on the coefficients of this function.
Okay, you are dealing with some functions, that's fine. But in the same time, you are talking that you have Calabi-Yau threefold sum. Let's assume that it's ample divisor, and then what do you compute? You compute probably, I can guess.
Compute this generating function. Well, in the end of the day. So this will be some concrete function.
You start with, so I'm not an expert in modular forms, and there are some textbooks on that. But you start with some geometry and you write some generating function for, I don't know, like number of semi-stable shifts somewhere. You even didn't explain where. Is it possible to see this generating function so we can look at it? And then you explain how you rewrite it so it becomes that explicit.
Okay, so what I showed so far is that, so what I did so far, let's recapitulate. I defined some generating function of rank 0 DT invariance, okay? So this is what I have done. Then I claim that one can derive certain restrictions on this function, namely that it must be modular or mock modular with some precise properties like modular weight, multiplier system, and so on. So these are restrictions. Then,
all right, okay, I understand.
Then providing some additional information, which I would like to explain you how to compute, one can fix these functions using all these restrictions. And actually now I'm trying to explain this, but before but since I wanted to explain also how I fix this function, at least the idea how I fix it, I need to introduce also some generalizations, because these generalizations are used in the process. Okay?
Well, it's
Oh,
not okay, of course,
oh,
mathematically, because as you explained, this modularity, it is something which it's impossible to understand mathematically.
why?
It's some whatever presence of SL2Z, mysterious, and so on, so on. So this link, but you want to generalize, okay, from ample divisors to effective. That's fine, but
This is not so important, but the next generalization will be important. I didn't talk about it yet. Well, at least okay, it's important for
Let me
solution.
explain you. As a mathematician, I'm interested in enumerative invariants, all right? So I don't care about duality in string theory. For me, it's just motivation, intuition, whatever. So when you say generalization, what do you mean?
Well, I mean that this statement, this expression for the completion, was derived using some assumptions, like I said, compact Calabi-Yau ample divisor, and well, then
I even do not see that. You
because I didn't
said some
explain.
words,
Uh,
but I don't remember that you needed ample divisor
because
anywhere.
I didn't explain the derivation. Of course, I explained
Yeah.
just in words, but I didn't show you the
Oh,
details.
okay, okay. So
Yeah, of
if you
course, there are
will,
many,
then
many
that's
details.
fine.
It's complicated, very complicated generalization. It's a huge work, but I
Not
showed that.
generalization, just a starting point. You start with something, and I would like to have something on which I can step, and it will not go away. So some starting generating function, which you derive from whatever Calabi-Yau threefold and what ample divisor in it. All right,
Oh,
and what do you
so you
compute?
want a concrete function? Okay, let me.
Not concrete, the definition. You start
Well,
with
the definition was. I'm sorry. The definition was this. Sorry, which slide is it?
what?
Oh,
Whatever, 2A, 2B type string
no, the
theory,
definition was
it
here.
didn't help.
The,
Okay,
this
okay,
was the
okay,
definition.
okay. Okay. So you assume that somebody gives you Donaldson-Thomas invariants. Okay.
No, I don't assume that in the sense. Well, I assume that you can define them, and
All
then
right.
my role is to compute them. Okay.
Uh, okay, and so the logic is that whatever generating function is your okay, yeah. But why amp? Why the divisor has to be ample? Can you recall it?
This is just technicality which was needed for the derivation. Okay.
Why do you need it? You need that that
Well, for
something will
example,
be convergent or what?
yeah, for example, if p cube is equal to 0, then there are singularities, and well, like I have them this p cube
Okay.
in denominators, and I have to study carefully how what happens if it becomes 0. So
Mm-hmm.
it's okay.
Okay.
So it's
All
just
right.
technicality. And
Okay.
compactness of Calabi-Yau I need from because I started from it was my physical picture of compactification. Yeah, I have this justification for its duality only in principle in the compact case.
Okay. Okay.
But
All right.
now, what I want to say is that, yeah, so first of all, sorry, how? Uh, so,
Okay, okay, you recall it. I mean, the
mhm,
most interesting step is mathematically not justified, at least in your talk, but up to this step, yeah. All right.
yeah,
Okay.
so then because once we have compact Calabi-Yau, we have that quaternion Keller modular space, and then we have this requirement of the symmetric action of cell to Z, and we have the derivation of this equation. Now, okay, now I'm sorry, but we will lose ground under our foots because there are two additional generalizations which are, do not have even physical justification. Not saying about mathematical, but somehow they do hold and they allow to get results. So one generalization is that we can actually consider non-compact Calabi-Yau. For example, we can start Calabi-Yau, which is given by elliptic fibration. So take elliptic fibration and take the limit of large fiber. And then what we get in the end, we get Calabi-Yau, which is given by total space of canonical bundle over a surface S. So this, if this was fibration over S, yeah, over S. So then we get this Calabi-Yau, and then, well, in principle, it's possible to define DT invariants also for this non-compact Calabi-Yau, and the claim is that this equation and the modular properties also hold in this non-compact case. And moreover, in this case, we have a duality with Vafa-Witten theory, because okay, DT invariants on this Calabi-Yau, they actually equal to the Vafa-Witten invariants on for the so if we take rank 0 DT invariants here for the sheaf which corresponds to well, roughly speaking, we take PA, so our divisor dP is equal to NS. So where n is just integer number, so this corresponds to SUN Vafa-Witten theory on S. And DT invariants equal to Vafa-Witten invariants. For those who don't know, Vafa-Witten theory is just some topological gauge theory defined on a four-dimensional surface, and there are associated topological invariants. And here I'm saying that rank 0 DT invariants are actually equal to this Vafa-Witten invariants. So this is one generalization, and another generalization is that actually we can also do refinement. Well, namely, we can introduce, so here I prepared a few equations, so we can introduce the so-called refined DT invariants. So in the case where DT invariant, well, in the simple cases where DT invariance equal to the earlier characteristic of some modular space, so then refined DT invariance just corresponds to the Poincare polynomial of this modular space, so it's just written in terms of bit numbers. So, and there is this refinement parameter y, which enters the game. So now these invariants, they start depend on this parameter y. Actually, in the compact case, it's not clear that one can properly define such things, as I understand, because it's not clear whether they will be invariant in the topological sense. But for non-compact Calabi-Yaus, it is possible to do. And then you define them, you define the rational version, and you define a generating function in a similar way, but note that I have this additional denominator here, which means that my function actually in the unrefined limit, which corresponds to y goes to 1, it has a pole, simple pole. And the claim is that one can generalize all that story also to the refined case, and in this case, this generating function, where z is the logarithm of the refinement parameter, it becomes actually high-depth mock Jacobi form, where z plays the role of the elliptic parameter. So it must also transform under S duality. Why it is so, it is not clear. There is no even physical justification for this statement, but somehow mathematics works. Somehow you can generalize all the machinery, and one can write a similar expression for the modular completion of this guy, and the coefficients in this case are even simpler somehow than in the non-refined case. So here I wanted to explain you the structure of these coefficients, but okay, let me skip it. If you wish, you can then look at this slide in the file which I'll send you. So, but there are some other certain trees, there are generalized error function entering the game. Okay, so let me skip this part. Yeah, just in the end, the unrefined limit is obtained like this. So you take the limit, y goes to 1, and you see the non-trivial thing comes from the fact that because we have these poles in the generating functions, so here we get a pole of order n of order n, whereas here the pole is only first order, here of order n. So it means that to produce something sensible, this coefficient should have 0 of order n minus 1, and well, only then this limit is well defined. In fact, it does. This ensures the consistency of the construction, and you can now understand why the unrefined coefficients are actually more complicated than the refined ones, because you have to apply the L'Hopital's rule to evaluate this limit, and this produces many terms which are absent in the refined story. This is why refinement is technically much more easy. Okay, then I would like to make the statement is that we can consider this expression for the completion as an equation for the generating function and try to solve it. And namely, we must look for a holomorphic function, because this is a holomorphic function, such that the right-hand side here produces something modular. And this is actually non-trivial, but can be done. And since, I'm supposed to explain only the idea, so I cannot go into details and explain how this can be done. But the claim is that you can construct a solution for this generating function in terms of indefinite theta series, which is very natural because the coefficients here are given by indefinite theta series. And what you remember, when I explained indefinite theta series in the completions, I mentioned that for null vector, if you have a null vector, then something special happens. And here you must have a null vector in your lattice to construct a solution, to be able to construct a solution, because the null vectors, only having null vector allows to write a solution. And if you don't have a null vectors, then you have to do certain tricks to get them. But in the end, it is possible to write a solution in terms of null vectors and indefinite theta series defined by these null vectors. And also, I recall you that null vectors generically, they lead to divergences, and only the presence of refinement allows to get finite results. And this is why refinement was also crucial for me, because only having this generalization to the refined story allows to write solution in terms of indefinite theta series. So, but in the end, the claim is that it is possible to write a general solution of this equation, at least in some particular cases. Which cases has been considered? Well, the cases which correspond to Vafa-Witten theory on rational surfaces, on S rational, and also considered compact Calabi-Yaus with B2 equal 1, so 1 Keller modulus. So these cases have been completely solved. Now, what about the solution? The point is that when you solve a modular anomaly equation, well, suppose you found a holomorphic function which makes this right-hand side modular, then it's clear that you can still add any holomorphic modular function and it will still be a solution. So it means that once you have a solution, general solution has an ambiguity. Which is given by holomorphic modular form. If you have a refined story, then this ambiguity is still restricted by the fact that it must have unrefined limit. And this is very non-trivial. Not the ambiguity must have the unrefined limit, but the whole function, the whole solution should have the unrefined limit. And it turns out that the indefinite theta series, which provides kind of the non-trivial part of the solution, actually typically does not have it. It has poles. And then you must tune this holomorphic modular ambiguity to cancel the poles of the indefinite theta series. And together with the modularity restrictions, this allows very often to restrict this function up to a finite number of parameters, essentially. And this is what happens in this Vafa-Witten story. For compact Calabi-Yaus, we actually, as I mentioned, we do not have proper definitions of refined DT invariants, and therefore we cannot apply this refined technique there, although we can still write a solution.
So for what you do not have, what you cannot define?
Well, at least I don't know whether
No.
what are refined DT invariants for compact Calabi-Yaus, and how to restrict them.
Since almost any word which you said has no mathematical meaning, it's difficult indeed to say what you cannot. But if you there is kind of a general theory of DT invariants for Calabi-Yau, compact Calabi-Yau 3 categories. So I don't know kind of what you cannot define. Maybe you cannot compute or prove something. So you have, if you believe, I mean, if you near large volume limit cusp, so you have the corresponding T structure and you count semi-stable objects with respect to, it's called weak stability condition, I believe.
Are they independent of the complex structure?
So if you ask about proofs, it's different. You said that you do not know how to define. It's difficult to define that any Donaldson-Thomas invariants which appear in your talk independent on complex structure. It's hard mathematics. But if you believe that they are, because the definition is universal, it does not depend on details, yeah. So then,
so I understand even from the physics point of view, we do not expect refined DT invariants for compact Calabi-Yau to be independent of complex structure.
refined, of course not, because it's like Hodge polynomials. Of course they depend. Yeah, it's not
This is
it's
one
not a
of the
question.
problems.
If you are talking, but they do depend, but then they change somehow, like Hodge numbers change when you move along the modular space of complex structure. It's exactly the same phenomenon. Your index or whatever Euler characteristic doesn't change, but the actual Hodge numbers, they do. So that's I do not see it's pure mathematical phenomenon. But to define it when the complex structure is fixed, I don't see a problem. I mean,
well, maybe
mathematical question.
another problem is that we also actually do not know the precise modular properties, because in this case, these are Jacobi or mock Jacobi forms we expect, and they are characterized by a weight and also by the index, right?
So,
Jacobi
listen,
forms.
this I don't know. In your exposition,
But I'm saying
any kind of modularity comes from higher physics, which no one in the audience understands well.
I repeat, in the refined case, it doesn't come in from physics; it comes from sky.
Whatever, sky or not sky, I don't know. I mean, from whatever. What mathematically I can understand that if you consider the derived category of coherent shifts on the Calabi-Yau, then there is a big discrete subgroup, like for elliptic curve, for example, like something like SL2Z acts by autoequivalence. These mathematicians can understand. And maybe the modularity is related to the action of this discrete group. Yeah, but again, it should be probably it's been studied, so I did not follow to all the papers, but there should be some mathematical explanation. There must be mathematical explanation because there is a definition of a generating function. You are asking whether it depends on the complex structure, whether there is a modular property, and blah blah blah. All that mathematical question that can be formalized. Yeah,
sure.
so
Consider this what I'm presenting like a prediction for what you're supposed to discover.
Okay, maybe it's been discovered. I don't know. As I'm telling you,
I'm not sure. No,
it's
I think this.
in industry now
Yeah.
of work. Okay, go ahead.
I think this modularity for generic Calabi-Yau or compact Calabi-Yau hasn't been understood. But refined case is even more complicated. It's not even understood from physics point of view. And what I want to say is that even we do not completely understand modular properties because you see in this index, so there is a first term which is completely fixed. It's just a concrete number for each Calabi-Yau. But then there is a second term, and it contains this coefficients lambda a, which is supposed to be integer numbers, but we do not know what they are. We know what they are for Vafa-Witten story, for example, for non-compact Calabi-Yaus, but not what they are for compact Calabi-Yaus. So even we cannot fix completely the modular properties. And therefore, once we cannot fix them, how can we find the generating functions? Okay. So, but let me return again to the problem of compact Calabi-Yaus and explain how we fix this modular ambiguity, because there is a method to fix the modular ambiguity. And the method, so here I skip many things. So the method is based on the wall crossing. Because, yeah, you remember I told you, first of all, this modular ambiguity, so for each charge, this modular ambiguity is just a weakly holomorphic vector-valued modular form. And you remember I told you that the space of these modular forms is finite dimensional. This means that it's enough to fix just the polar terms or first coefficients in the Fourier expansion of this generating function or the corresponding this ambiguity, the weakly holomorphic modular form, and you will fix it completely. So therefore, what we need to do is to compute the first few terms in the Fourier expansion of our generating function. Can we do it? And it turns out that sometimes we can using wall crossing. And here you remember last time we discussed a bit stability conditions, and here the claim is that the physical stability condition, if you live just on this physical slice, which is described by holomorphic prepotential, it's not enough. But there is a method which allows to do what we need if you go to this larger space of Bayesian stability conditions. Why? Because, well, here I kind of drew schematically this space in the one modulus case, more precisely some two-dimensional slice of that space, which in general is four-dimensional, but I cannot draw four-dimensional space, right? So on this slice, you see there is a physical slice in blue, but then there is a larger space, and it was constructed more or less rigorously by Bayer, Macri, and Toda. So we have its description. And in my parameterization, the large volume point is in the beginning. And the claim is that on this larger space, there is another slice, which is kind of nicer than the physical slice. It's called new BW stability. And it lies somewhere at the boundary of this space. You see along the horizontal axis. And why it's nice? Because, well, first of all, here I put a description of this stability condition. So it's defined by this central charge function, where A and B are like our moduli, our parameters, which we can vary. They parameterize the different stability conditions. Then this Chern class is shifted by B, just defined like this. And why it's nice? Because it turns out that once we live in the stability conditions, to have a non-vanishing DT invariant, the following inequality must be satisfied. So it is called BMT inequality. BMT T inequality. A squared over 6 churn 1b. And if this inequality is spoiled, we are sure that the DT invariance should be 0. And it turns out that for some charges, indeed, this inequality is spoiled somewhere here. You see, I put that omega gamma is 0 here. Not for all charges, but for some charges. In particular, for charges which correspond to, for example, for charges which have P0 equal -1, so rank -1 DT invariance, they also have the name Podkharipande-Thomas invariance, so they call PT invariance. And then the idea is very simple. Let's start from here, from this chamber where the invariant is 0, and let's go to the large volume point. And on the way, we just apply the standard Wall-Crossing formulas. In most cases, just a primitive Wall-Crossing formula is enough. And in this way, you can compute PT invariant at the large volume. And it turns out that, well, I will write schematically. So roughly speaking, this PT invariant, which we're interested in, will be given by a sum of PT, other PT invariants with charges gamma prime, but which are typically, well, in certain sense, they're less than gamma. And our invariants, omega, P, mu, so rank 0 DT invariants, Q0 hat. Well, some P prime also, or P double prime here. So the idea is that there is a kind of formula of this type. And it turns out that in this sum, there is always a term which, well, roughly speaking, gamma prime correspond to the charge like -1, 0, 0, 0. Or, well, in terms of Chern classes, in terms of physical charges, there will be some rational coefficients appearing here. So, but what is important that for this guy, PT gamma prime is equal to 1. So it's always trivial. Yeah, of course, here there is gamma prime also, a factor in this formula. So this is just primitive Wall-Crossing formula. And then you can pick up the corresponding factor, you pick up this term with this trivial PT invariant, and it contains as a coefficient some omega, and just put it on the left, and this PT invariant on the right, and in this way you obtain explicit formula for rank 0 DT invariant. So there is a way to rigorously obtain a Wall-Crossing formula expressing rank 0 DT invariant in terms of PT invariance. And maybe other rank 0 DT invariants, but of lower charges. Okay? And then, so this is a way to obtain, to compute this rank 0 DT invariance. Of course, the larger we want to have, or, well, more precisely, smaller we want to have Q0 hat, the kind of PT invariance of high degree we will need. So that's typical situation. So if we want to compute, so in other words, more terms in the expansion of our generating functions we want, high degree will be needed of PT invariance. So you see, at this step, we reduce the problem of computing rank 0 DT invariance to the problem of computing PT invariance. Is it better? Yes, it is, because for PT invariance, there is a method to compute them using the so-called MNOP formula. So what is it? The point is that, so let me remind that there is the so-called topological string theory, which computes some objects, which are called genus G free energies of this topological string. And in general, these are non-holomorphic functions of the Keller modular of the Calabi-Yau, but in the so-called holomorphic limit, where you just remove anti-holomorphic part of that, these free energies, they reduce to the generating functions of Gromov-Witten invariants. And it turns out that these generating functions, well, if you collect them into, you sum over genera, so you define what is called topological string wave function or partition function, then there is a nice formula, nice result due to Maulik, Nekrasov, Okounkov, and Podkharipande, which relates this topological string free energy to the generating function of PT invariance, which is defined, well, simply like generating function. And the coefficient is the so-called Mach-Machen function, which is defined here. So there is a relation which allows to trade PT invariance for Gromov-Witten invariance, you see? In fact, it's better to work not in terms of Gromov-Witten invariance, but in terms of the so-called Gopakumar-Vafa invariance, because Gromov-Witten invariance, you know, they are rational numbers, and Gopakumar-Vafa invariants are integers. So in other words, instead of this simple function, you express psi top like this series. So this is the so-called Gopakumar-Vafa representation of topological string. So in other words, you can trade PT invariance for integer Gopakumar-Vafa invariance. So if you know somehow GV invariance, you can compute PT invariance. So that's the moral of the story. And if you want to, just a small comment, if you want to do it in practice, better use not the formula which I showed, but a slightly rewritten formula, which is the so-called plethistic form of the OMNP relation. Is much, much more efficient, at least on Mathematica. Okay, so now we reduce the problem to computing GV invariance. Can we do it? Yes, we can, because there is a general method of solution of topological string theory, which is called direct integration. So so what is it? The point is that this psi top, it satisfies certain holomorphic anomaly equation. And there is a general method to solve this equation, and which is precisely called this direct integration. And you can do it genus by genus. So you start from genus 0, genus 1, genus 2, and so on, and you continue. Of course, so similarly to what we have in our story, when you solve an anomaly equation, the solution always has an ambiguity. In this case, the solution has a holomorphic ambiguity, because you can add any holomorphic function to the solution, it will still satisfy the equation. So then, but fortunately, this holomorphic ambiguity is parameterized by a finite number of parameters. At each genus, at fixed genus, of course, at fixed G. And fortunately, we know kind of, if you wish, boundary conditions which allow to fix this finite number of parameters. So we know some number of conditions at each genus. But the problem is that the number of known conditions with genus grows slower than the number of required conditions. And at some point, the two curves cross, and there is certain maximal genus beyond which you cannot go. You cannot solve topological string using direct integration beyond certain maximal genus. And this happens for any compact Calabi-Yau. So the moral of the story is that you can find GV invariance up to certain Gmax using this direct integration. And then once you know GV invariance up to Gmax, the MNOP formula allows to compute PT invariance up to certain Q max. Q is the degree. So up to a certain degree, you can compute PT invariants. And this implies that you can compute some terms in the expansion of our generating function. And sometimes you can compute all polar terms, sometimes not. So it depends already on the concrete Calabi-Yau. So let me briefly flash you the results of what we have done. So we consider it a set of one parameter Calabi-Yaus. So one parameter complete intersection Calabi-Yaus. So there are 13 Calabi-Yaus like this, 13 models. And for 11 of them, for 11 such Calabi-Yaus, we managed to find all polar terms found, all polar terms for the very first generating function, which is h1, and which is h1 mu, which is not mock modular yet. It is just modular. You remember for the irreducible divisor, we have not mock modularity, we have the standard modularity. So in this case, we managed to find, so for 11 Calabi-Yaus, we managed to find this generating all polar terms and hence the whole generating function. And actually what we have done, we computed not all polar terms, but also some non-polar terms. We went using these wall-crossing ideas, wall-crossing formulas, we computed also some non-polar terms. And they precisely coincided with the expansion of the resulting modular form, which we computed on, based on the knowledge of only polar terms. And this provides a very striking test of this S-duality. Because you compute the same huge number, sometimes they have, I don't know, 30 digits, you compute it by very two different methods, and you get precise match. So for me, it's a really very non-trivial test of S-duality. And moreover, we actually did better. We went to the charge 2, so H2 mu, which is already mock modular. And for two Calabi-Yaus, we managed to find them. So there are two Calabi-Yaus, the so-called X8 and X10 models, for which we managed to find this H2. And also there we computed also some non-polar terms and they perfectly matched. So there is already a striking test of not only modularity, but also mock modularity. And these are probably the first mock modular functions associated to Calabi-Yaus without any structure like elliptic fibration or K3 fibration. So here I just, so Jan wanted to see some concrete functions. So here they are.
Well, I would be happy to see them before, because now it's absolutely useless. It's some numbers which
because
will, that's why I asked you to set something before, but you chose this way, so certainly I'm lost in this. So these numbers do not convince me in anything, because some coefficient can be wrong. I should look at them more carefully. Yeah.
I don't know how you are going to check this coefficient, but well, then you have to go
at least
through our
theoretically I can. Now I can just watch.
Yeah.
It's, you know, it's like TV program.
Okay, but the point is that we, for example, these coefficients we computed by two methods. One method, well, is simple. Is you just take this function and expand it. Yeah, this is one, and this function is now is found on the based on the knowledge of modular properties and the knowledge of these terms in blue, which are polar terms. And on the other hand, you can compute the same terms, the same coefficients, using these wall-crossing formulas which I mentioned. And
actually, Sergey, I'm sorry, because I was called, so I was away for a while. And so I understand it's a very old idea how to use wall-crossing formulas to compute something in the interesting region, blah, blah, blah. But often there are infinitely many walls from the region where your, I don't know, DT invariants or PT invariants, depending on the
Here,
situation.
everything is concrete.
They are trivial, but then when you want to go to some interesting regions, typically you have infinitely many walls, and it's difficult. How you?
No. Here, everything is concrete. There is a very concrete formula which relates these coefficients here to PT invariance. Very concrete, with finitely many terms, which come from finite number of walls.
You see, so it looks like you're kind of, I mean, I understand you're a physicist, but
This is done
you explain
not by
things
thesis. Yeah.
which are not that interesting for mathematical audience, but you skip the most interesting parts, and actually, so you start, for example, in the area where all PT invariants are equal, say, to 1. I don't know. How you do, I mean, this wall crossing formula, they're quite complicated. How you
probably missed this part, right?
probably, yeah.
Yeah, so this is the part which I explained that there is a region where PT invariant is 0 because it must its charge spoils this BMT inequality, and then you do wall crossing to the large volume region, and you can compute this wall crossing. Typically, this is just application of primitive wall crossing formula. Not all this, but in most cases, and there are finitely many walls, and everything is explicit. And this is done by Sergey Alexandrov, who is a mathematician. So she did.
In what
She has done everything
generality? In what generality for compact Calabi-Yau?
For compact Calabi-Yaus with one Keller modulus.
Yeah, it would be, of course, nice to see those formulas. But what is your nice region where omega of gamma is equal to 0? Is this your nice region?
Yeah, this is the region where this inequality is spoiled. It does not exist for all charges, but for some charges.
All right, but then if you want to go to large volume chamber, then it looks like you should pass through, you say finitely many, I don't see why, but some through this physical modular space or whatever, or at least at the boundary, where you have very strange invariants, which are stable invariants and some yes.
In the large volume, they coincide with the physical ones, which we're interested in. That's the point. So here the two slices coincide. The physical
all right.
slice.
So yeah. So okay. Mathematically, then the most interesting part is indeed this formulas how to you recompute your DT invariants on the way to large volume limit. I don't see it. If it's done by someone, it's very interesting.
This is done by mathematicians, so
that's good, but you should not expect that I read every mathematical paper.
Yeah, sure, but I at least try to explain the idea. So
all right,
idea
but
this calculation.
all right, that's okay. So you compute, but again, this modularity does not hold in wall crossing when you do this wall crossing business or what?
No. The wall crossing is used to compute. So the logic is the following. First, we have generating function with some fixed modular properties. Suppose it's mock modular form. Then we solve modular anomaly and find the corresponding mock modular form up to a pure modular form, right? But pure modular form can be fixed by finding a finite number of first coefficients. first Fourier coefficients. So wall crossing is used precisely to find this finite number of first coefficients. And the logic is the following. So let me actually draw a picture. Here. So the logic is again, I start from solution of topological string theory, which topological string, which allows to compute GV invariants up to certain genus, G max. So this is done using the so-called direct integration. Then from these GV invariants, I use MNOP formula to compute PT invariants up to certain Q max. Q is the degree, up to certain maximal degree. Beyond, I cannot go. Then I use these wall crossing formulas to compute some finite number of rank 0 DT invariants. And then, using modularity, I can restore the full function. So that's the scheme.
That's helpful.
Yeah. Now, actually, the good news come even better. Suppose we have explicit examples, as I showed you. We found some examples of these generating functions, and we can expand them. So in this way, we can produce actually infinite number of rank 0 DT invariants. So we can go back, and now we use exactly the same wall crossing formulas to compute new PT invariants and then new GV invariants. And in this way, it turns out that the data which you can compute out of this information actually allow to go beyond G max. So in other words,
what is G max?
G max, I explained when you were absent. This direct integration of topological string works only up to certain genus. For each Calabi-Yau, there is certain maximal genus beyond which you cannot go because you don't know boundary conditions which allow to fix holomorphic ambiguity. And you are just stuck. You can, in principle, you cannot go if you don't find any alternative way to find boundary conditions. And what I'm saying is that this approach, it produces new boundary conditions for direct integration.
So it doesn't say me anything. So is it expected?
It allows, in other words, you can overcome limitations of this method, which allows to compute a GV or Gromov-Witten invariants. So I'm saying that with this information, you can go beyond the standard limitation. You will still get some new restriction, some G max prime, let's say, but you can shift this boundary further and further if you compute more and more these generating functions.
Is it expected that this generating function is an expansion in particular of an analytic function in genus?
No, there is no genus in this generating function, sorry.
What is G max? You said that it's a bound for the genus.
Because topological string is about computing some free energies for each fixed genus, right? So
yeah, all right, but then you can consider the generating function over G, correct?
Yeah, it's topological string.
That's what you, okay, very well. So what I'm asking you, whether it is expected that there is analyticity in genus, and so in particular, if you know something for infinitely many values of G, maybe you already know, at least in the theory.
I mean, whether FG is analytic in G.
Not FG, but maybe
which object?
I don't know. Maybe this topological expansionless exponent is in fact. I don't know. Or maybe FG. No, probably FG.
No, FG.
If G is an.
No, it will not be. I wouldn't expect so.
Okay.
It's like generating functions of Gromov-Witten invariants should be analytic in G. Well,
maybe it's not, but I don't know. Maybe it's resurgent, so I can resum. I don't know. I'm not a physicist. I'm asking.
Yeah, you do expect resurgent structure, of course, for this guy. Yeah, that's for sure.
If
Marcos
research,
Marinho studied
FG, I mean,
no, G is the summation parameter, so you expect, well, it's like resurgent structure precisely for this series. So there is a divergence for when G grows, and yeah.
Yeah, but the question was what kind of divergence, whether it's controlled divergence or then
Yes, it is controlled. Well, Marcos Marinho produced, I don't know, dozens of works about this resurgent structure of topological string. So
okay, very well. But then if you know that it's resurgent in the genus, then probably you can do the resummation, get some analytic function. And if you know analytic function on insufficiently many points, then you
I'm
know
not
it
sure.
everywhere.
I'm not sure anybody was able to produce any analytic function for topological string on compact Calabi-Yau. That's out of reach so far.
That's true. Okay, agree. But
Yeah.
you mentioned something about non-compact, and that's, or maybe that's what
Well,
I
for
mean.
non-compacts, probably yeah, there are results for some simple non-compact
Yeah,
manifolds, but again, I'm not sure. Yeah,
okay, for
how.
compact, probably it's even not true because the
Mhm.
growth is very fast. Yeah, okay. Okay, thank you. Yeah.
Yeah. Okay, so just maybe since I mentioned that we can raise these limits on genus. So just to give you an example, so for example, for this guy, for this X10 manifold, for which we computed H2, so the standard limitation like G max is equal to 50, and we already computed GV invariance, which means also Gromov-Witten invariance up to G equal 71. And the new limitation for us, G max prime, is like 95. And for quintic, so X5, the standard limitation G max is 53, and we already have G64. And the current restriction for us is 69. Just didn't go to the maximally possible. Okay, so that's the main message. So one of the main messages is that using modularity, you can compute generating functions of rank 0 DT invariance, and this in turn can be used as an input for computing also Gromov-Witten invariance. So then, well, in principle, my time is over. I wanted to present two other things. One is maybe I just flash. It's ongoing work with Albert Clem and Boris Perlin. We just studied, since we produced big tables of these invariants, we studied the asymptotics, and it turns out that if you study asymptotics of PT invariants, so log of PT, for all these one parameter manifolds, and take large degree, and so here you change the degree, so the different curves correspond to different degrees, and the horizontal axis here is the what we call D0 brane charge, Q0. Essentially. So you see that there are some kind of, so you get almost smooth curves, and there are some nice, interesting phase transitions happening. So there is interpretation for this phase transition here, physical interpretation, but these ones are new, and we don't understand them. So I don't know, maybe for some mathematicians it will be, so these facts will be interesting. I don't know. And another thing which I want to tell you is some puzzle. So if you wish, I can tell you, or I'll stop here. So I have a puzzle for you.
I mean, it depends. You see, it's like what puzzle about what?
About wall crossing.
Okay, you can say in few words, yeah.
Okay, so here. Okay, let me start here. So I told you that the wall crossing which I use for my calculation was I expressed PT invariant in terms of gamma I, gamma J here through other PT invariants say gamma I, and my rank 0 dt invariant here, 0 dt. But there is another wall crossing which you can use. Namely, you can take rank 0 dt and express it like a bound state of d6 and anti-d6. So which means that here there will be gamma gamma prime, and here there will be pt invariant of say gamma and dt, the canonical dt, which means rank 1. So this is rank -1, and this is rank 1 dt invariant, gamma prime. And the point is that, again, you can find the empty chamber for this guy, namely a chamber where it spoils this BMT inequality, but it's very restrictive on the charge. So this guy depends on charge. So almost typically you can find such empty chamber only for like the most polar term in your generating series, but already the second term will spoil the condition and it doesn't hold. So in other words, you can derive such a formula for like this, but typically its area of applicability is very restrictive, so on charges. But then since we computed some of these guys, we can just check what we get. And it turns out that this formula works in almost all polar terms. For example, for our 11 Calabi-Yaus, which we considered, in total there are 72 polar terms, and it turns out that for only 8 of them this equality is spoiled. So only for 8 of them it doesn't hold. So it means that there is some truth in this guy. And one example is particularly interesting. This is precisely this X10 manifold for which we could go to charge equal to, and H1 in this case takes particularly simple form. So it's just a scalar.
What is X10? Sorry, because it's
X10 is the manifold. It's a complete intersection Calabi-Yau, which is okay, let me find. So it's embedded into projective, weighted projective space. So like, so maybe in these notations will tell you something.
No.
Well, okay, so this is like what? This is like, okay, this is projective space of how many? I think 4 with these weights. Sorry,
you know, Sergey, it
okay.
becomes
It doesn't
maybe it doesn't matter. Is it in your review paper in the archive?
Yes.
Okay, so maybe just refer people to that review paper, which is more or less has the same title as your talk, because you see, if it wasn't so unprecise before. What I get that there are 2 types of wall crossing formulas which you use, but I mean,
exactly.
To fix the polar part. So that's interesting, but for me, kind of the whole scheme is a little bit mysterious, and maybe not a little bit.
The puzzle is not about that. The puzzle is about just one term, okay? Actually about more terms, but for one, it's particularly interesting. So there is this term, which we know its exact value because we computed it using another wall crossing. But the point is that if you use this formula, you get another number, you get 576. Well, you say
it's
so
close,
what? Yeah, it's close. And anyway, this formula is not expected to hold because, this condition for this empty chamber is spoiled. So you don't expect this formula to be true anyway. But then there are 2 works by physicists many years ago, like 15 years ago. So let me just give you the numbers. where they considered the problem of, in particular for this manifold, in particular in this second reference, and they found a way to produce the right number. And the way
right is 576.
575.
575.
Yeah,
Okay.
and the way they did it is very weird. And so the puzzle is why it works, whereas it shouldn't, and it doesn't make any sense. But
okay.
they not only produce this number, they produce many other numbers. So there is some truth in their method. And the method is the following. So they say that in this formula, so what is this? These are dimensions of some modular spaces. So they call it MT, I don't know, this anti-D6, MD6. So these are some dimensions of some modular space. In particular, there is this one, MT. So the T is because they related to some tachyon, some field in string theory. It doesn't matter. But what they say is that if we study how this, so these modular spaces, they actually, well, the idea is that there isn't just direct product of them, but in fact they claim that the spaces are fibered over each other. And as a result, this MT, sometimes there are points or loci on the Calabi-Yau where this MT changes its dimension. And therefore, instead of the primitive Volkrossian formula, one should use its weird modification. So where there are different terms, so roughly speaking, you take this term plus another term of the same form, but the value of this coefficient will be different. And in this weird, and what, so essentially what this comes from the wrong interpretation of this coefficient, because what they did, they took this, gamma prime.
I think it's so technical and so impossible to understand for people who did not even look at those papers. Then, okay, you can finish this formula because it has some mathematical meaning. Yeah.
Yeah, precisely. I wanted to show this formula because because the construction is based on this assumption that this coefficient is given by this dimension, whereas, as I understand, the correct mathematical fact is that it's given by this, right? Gx and E1, E2, right? This is the earlier pairing of the two classes.
Well, it should be, yeah, the last formula should be true, but for some reasons, you know, if some other are equal to 0, they cannot be all equal to 0 because of Calabi-Yau pairing. X1 is dimension of X1, I mean, it's related to dimension X2, but yeah, maybe there is, in this particular example, you can get rid of others. So you have X0, X1, X2, and X3. And
exactly. So that just, okay, let me say, what happens is that at most points, indeed, most of xn's are 0, and you reduce just to this formula. But there are loci where, let's say, x2 is not 0. And but what happens is that this guy is always constant, whereas this changes. It takes different values on different loci. And they took wrong formula for this coefficient, and they saw that it changes values, and therefore, instead of kind of one term, you should write two terms here. But going in this wrong way, they produce the right number.
Yeah, you see, so I understand that it's possible. You know, like there is this funny story about the guy who won a lottery because he thought that 7 by 7 is 47. You see, they can produce the right number, but in order to see whether this formula holds or something wrong in the computation and the Volkrow, it's impossible. It's a puzzle. You gave references. Thank you. It's one can look at it and see their computations and to see whether they made mistake or they did not. So it's of course
I repeat, they produce not just one number; they produce several numbers, and
all
some.
correct. This means that probably for some reason this pairing is equal to is equal to minus dimension. Why it's equal to that? Then it's a different question because it's a very concrete example. Yeah.
Yeah.
And so in this particular case, it's possible that this formula is satisfied. What is
We did it for
written?
several Calabi-Yaus, so not just one case, several cases. And why I'm telling this puzzle, because if you understand it, then it can have far-reaching consequences. Because, as I told you, the previous method, based on just PT invariants, has some restrictions. You cannot apply it to many Calabi-Yaus. But
Okay,
this one is
Sergey,
much more
I
promising.
think we should finish because, in particular,
Sure.
because I
Yeah.
have another meeting soon. All right. So, more questions from the audience. Well, if there are none, so let's thank Sergey for three inspiring lectures. And I ask you, I recall you sent me
Sure.
the notes of your notes. And this is it for today. And actually, next week we will have another seminar, but like mini series. But that time it will be a mathematician. So then at least we will be able to understand the words.